Today I want to show you what the magnetic field looks like around a bar magnet. We're going to use a compass in order to map out what the magnetic field looks like at each point, as well as iron filings. Iron filings are basically like little pieces of iron that act like compasses themselves. And when we place that around the bar magnet, you're going to see the magnetic field basically all at once. So what you see here is our bar magnet. Our bar magnet has an N and an S, designating this end being a north and this end being a south. So we have our compass as well. Now the thing about a compass is a compass will always line up with a magnetic field that's closest to it. So right now it's lined up with Earth's magnetic field, and you can see by the direction it's pointed. When we put the magnet back in place and we place the compass near the magnet, you can see that the red end of the compass is pointed towards the south and away from the north. And that's the purpose of a compass itself. The purpose of a compass is to point away from a north magnetic pole and towards a south magnetic pole. So if we were to place this compass around the bar magnet and then identify what direction it's pointed, for example right here, it's pointed this way. Here, it's pointed this way. Here, it's pointed this way. And then we can get a map of the entire magnetic field as we place this this compass around this bar magnet. So let's go ahead and do that. We'll do several places, and you can see what the magnetic field is going to look like. So now that we've mapped out several locations with the compass, you can clearly see how the around the north it all points away every single time, and around the south it points towards. So what you see is you actually get from north to south, the magnetic field will point away and then start pointing towards. So you get kind of a line that goes from north to south. Same thing on this side, from north to south. So all the lines pointing into the south and away from the north, that indicates the direction of the magnetic field. Now this is actually a convention because a compass itself only points away from a north, because we identify this end as being a north magnetic pole. So that end being a north magnetic pole means it has to point away from a north. Now because it's a convention, that means it doesn't have to necessarily be that way, but it makes it easier when we start talking about the direction of the magnetic field to say that it always points away from a north and towards a south magnetic pole. Alright, so what we have here are little iron filings. Little iron filings are basically little pieces of iron. And these little pieces of iron, you can see, are very tiny. And they basically act like little compasses themselves. So let's go ahead, and I'm going to put the compass or the magnet underneath so I don't get the iron filings attached to it. And then I'm going to map out some of the iron filings on here. So with the iron filings placed on here, you can see that there's a magnetic field that goes between the north and the south ends. Now, with close to the bar magnet, you see that the definition of those lines is pretty well defined. However, as you move away, you can see out here that it kind of gets a little bit hazy, a little bit cloudy, primarily because there's probably a lot that I put out here, but also because the magnetic field gets weaker as you move away. So stronger near the poles, and that's where you see all of them clumped up with a well definition of as far as lines. But then as you move away from the poles, it starts getting a little bit less defined, meaning it's not as strong. So this is what a magnetic field looks like around the bar magnet, and even though we can't see the magnetic field, the iron filings definitely help us give a good picture of what it looks like. The next thing I want to show you is the property of a bar magnet. You can see the bar magnet here, one solid magnet, but one of the confusing things is that in electricity you have positives and negatives, and those positives and negatives can have separate charges. You can have a positive over here and negative over here. The thing about a north and a south of a bar magnet is you never have a north without a south. So if I have this bar magnet here and I break it into pieces, right? It's believed by some people that you have, a north pole over here, and over here you're going to have a south pole. Well, the problem with that is if this is a north and that's a south, then if I put them near each other, they should attract. And you can see they definitely do not. Now the reason they don't attract is because what happens when you break a bar magnet apart is you actually get another magnet with its own north and south. And if this is a north and that's a south and it's going to attract to this, then that means for this little bar magnet, there's a north and a south there as well. And for this magnet, there's a north and a south there. So what you have is you have your north, south, north, south, north, south. Okay? Now if I take this middle one and I flip it around, that means I now have the south facing the south, and those two repel each other. And you can see it actually flipped around. Okay? Now with the north and the south facing each other, you can see that they attract. So this shows that when a bar magnet is broken up, it actually becomes more magnets. Now, one of the things we've talked about with a bar magnet is that it's actually made of a lot of little magnets, little itty-bitty magnets that are all placed together into one big magnet that gives us this bar magnet. Those little magnets we refer to as magnetic domains. So magnetic domains are basically like a bunch of little magnets within one big magnet. Now, if you align all of those magnets in the same direction, then you get something like a permanent magnet with a magnetic field is all, or at least mostly, all facing the same direction. Now, if you take these magnetic domains and you mess them up, and they're pointed every which direction, that is what's referred to as a material like this nail. This nail is called a ferromagnetic material. And the reason it's a ferromagnetic material is because it has magnetic domains, but those magnetic domains are facing every which direction. But if we come into the presence of a permanent magnet, then that ferromagnetic material will attract to it. Now that's the north end of the magnet. If I flip the magnet around and put it near the ferromagnetic material, it still attracts. Now the reason it still attracts either way is because the magnetic domains, when they're in random directions, then they don't have their own magnetic properties, because some of them are facing each other, some are facing against each other, and some of them cancel, some of them add to each other, so you don't get a full magnetic field. But in the presence of a bar magnet, then those magnetic domains will line up. And if they line up in one direction, then it'll attract. But if the other end comes toward it, you can see that they start flipping the magnetic domains around, and it still attracts. All right, so a ferromagnetic material, while itself is not a magnet, will attract to a magnet because it does have some magnetic properties.